In this lecture, we will study exact ordinary differential equations, and in part 2, we will study integrating factors. So let's start with some definitions. Definition: given a function f with continuous partial derivatives, the differential df of f is df is equal to the partial derivative of f with respect to x dx plus the partial derivative of f with respect to y dy. So, and sometimes we write it del f over del x as short as fx and del f over del y short as fy. So this is the differential df of f. Okay, then what is an exact differential equation? So let's say that we have a first order differential equation m dx plus n dy is equal to 0. Here m is a function of xy and n is a function of xi. And this ordinary differential equation is called exact if the differential form m dx plus n dy is exact. So what does this mean? So that is, it means that it is equal to the differential df of some function f of xy. So this is really nice because if it is a differential of some function f, then we can write this m dx plus n dy is equal to this differential df and it is equal to 0. Then we know how to solve this kind of differential equations. We just integrate, right? The integral of df is equal to f of xy and the integral of 0 is just the constant c. Then this differential equation m dx plus n dy is equal to 0 will have the solution, this general solution f of xy is equal to c is going to be its solution. So we just finding f will be enough in our case. Great. And we have a very nice theorem to check exactness. So we will use this theorem a lot. So consider the differential equation m dx plus n dy is equal to 0. So this is exact if and only if. So if and only if. Sometimes we write it like this, if and only if. The derivative of m, so what is m? M is the coefficient of dx. The derivative of m, the partial derivative with respect to y, so the derivative of m with respect to y is equal to derivative of n with respect to x. So n is the coefficient of dy. So you see that we take the coefficient of dx and we take its y the derivative with respect to y, and we take the coefficient of dy and we take its derivative with respect to x. It is just its opposite, right? So you can keep in your mind. And the proof of this theorem is very straightforward. So I will not give the proof here, but I would like you to check it from the book. And let's continue with an example, and you will understand how we solve the exact differential equations. So given this differential equation 2xy, okay, let's start with an easy one. 2xy plus 1 dx plus x squared plus 4y dy is equal to 0. Given this differential equation, show that it is exact. So the question is, show that it is exact, and then solve the differential equation. Okay, for exactness, what we check? So we say that, this is dx plus x squared plus 4y dy is equal to 0. And in this case, let's call coefficient of dx m, the coefficient of dy n. And we need to check that the derivative of m, the coefficient of dx with respect to y in this case. Sorry about the noise. Y in this case. Okay, maybe, okay, let me write what is m. M is equal to 2xy plus 1. Okay, then what is its derivative with respect to y? Okay, we think x as a constant. Oops, sorry. We think x as a constant, and its derivative is 2x. What about n? X squared plus 4y, and we will take the derivative of n. Since it is the coefficient of dy, we will take it with respect to x. So the derivative of n with respect to x is 2x. We think y as a constant. The derivative of 4y with respect to x is 0, right? So since, and the theorem says that the equation is exact. The equation is exact if and only if these partial derivatives are equal, and in our case they are equal. So since del m over del y is equal to del n over del x is equal to 2x, by theorem the equation, the differential equation is exact. The differential equation is exact. Then by definition of exactness, by definition, there is a function f, or let's say there exists a function f there exists a function f of xy such that so we know that m dx plus m dy is equal to, so this is our definition, right? Del f over del x dx plus del f over del y, so df is equal to 0. So this means that, so we have del f over the coefficient dx, so we should have del f over del x is equal to m, right? And which is, in this case, we have m is equal to 2x plus 1. And we should have del f over del y also. And so I think, sorry about that, I forgot to write dy here. So dy is equal to df is equal to 0. Okay, so, and now we also have del f over del y is equal to n. What is n in this case? X squared plus 4y. Okay, so, and we say that we set if df is equal to 0, then once we integrate f is equal to c is our solution. So using these two equations, we will find, so f is the solution, and we will find f using these two. Using these two, we will find f. Okay, let me copy it into the next page. Oops. Okay, then how we will find f? So we will just integrate. Choose one. So to find f, choose one of the equations. And integrate. So we will just integrate and find f. So if we choose, let's say choose this one. Okay, we choose del f over del x is equal to 2, I think I forgot y here, 2xy. Sorry about that, 2xy plus 1. So 2xy plus 1. And we will just integrate. So once we integrate, we have f of xy is equal to, so since we choose this one, we integrate with respect to x. Then what is the integral of 2xy? So we know that it is 2x squared over x y plus x plus. So usually we write constant c, right? But when we take the partial derivative with respect to x, we think y as a constant. So our constant is a function of y actually. So constant, let's say it is a function h of y. So since we take the derivative of f with respect to x, anything like in this case also, like we have 4y. So if we take the derivative of 4y with respect to x, it is 0, right? So we don't see it in the partial derivative. That's why we need to add a function of function of y here. And now how we will find y? We will use this equation. So to find h of y, use del f over del y is equal to n. So we know it is 4y, right? So use this to find h of y, right? So we will integrate, sorry, so we know f is equal to this one. Then we will take the derivative of f with respect to y here. And okay, we will cancel this one. So what is the derivative? It is x squared plus the derivative of x with respect to y is 0 plus the derivative h prime y. And we know this is equal to n, right? So this is equal to n, and it is given as x squared plus 4y. So now we can find h. Then when we cancel x primes, x squared, we will find h prime y is equal to 4y, and we can find h, we just integrate. So it is 4y squared over 2, so it is 2y squared. Then what is our function f? F of xy, or now we can write plus c x squared y plus x plus plus h of y, and we find h of y 2y squared plus c. But we said that f of xy is equal to constant c is our general solution. So let's write c1 here, and let's write c1 minus c as some capital C. Then f is equal to this capital C is our solution. right? So capital C is the solution. Let's say general solution of the given exact differential equation. So it is always the same idea. We will show the equation is exact, and then we will assume that such a function f exists, so that it is the differential. Its differential is this differential equation, equal to this differential equation. Okay, let's do another one. I think don't worry, we will solve a lot of examples. I hope you will understand what is going on here. Okay, let's continue. Example number 2. Okay, show that same example. Show that, same question. Sin x plus y dx plus x minus 2 cosine y dy is equal to 0 is exact. Show that is exact, and then solve. We will solve the equation. Okay, now how we show that it is exact? So we check. So this is n, and this is n. So m is equal to sin x plus y, and n is equal to x minus 2 cosine y. And we take the derivative of m. It is the coefficient of dx, so we take with respect to y, so which is equal to 1. And we take the derivative of n, which is the coefficient of dy, with respect to x. So here again it is 1. So since these are equal, since we have the equality, the equation is exact. So the equation is exact. Then we know that then by definition, we know there exists a function f such that m dx plus n dy is equal to df, so this differential, which is equal to del f over del x dx plus del f over del y dy is equal to 0. Sorry, I think I make it's a little bit messier. I hope you understand. Del f over del y dy is equal to 0. So this means that the coefficient dx and the coefficient dy must be equal, so that del f over del x is equal to m, which is in this case sin x plus y, and the derivative of f with respect to y is equal to n, and in this case it is x minus 2 cosine y. Now we know that, so we know f is equal to c is the solution, is the general solution. So we will, to find f, we choose, so to find f, choose one of these equations, one, and integrate. Okay, I will choose the first one always, so I don't know. and then we will just integrate with respect to x. So we will have f of xy is equal to, what is the integral of sine x? So we know it is minus cosine y, or minus cosine x, right? Sorry about that. Plus, what is the integral of y with respect to y dx? So with respect to x, so we are taking integral. So it is yx, right? Plus some constant. But since we take the partial derivative with respect to x, so y is also a constant, right? That's why the constants are a function of y. So let's say h of y. And we want to find h of y. So we will use this equation to find h of y. So we will use this equation to find h of y. So what we are going to do is we take the derivative of f with respect to y. So it is minus cosine x, the derivative is 0. Y times x, the derivative is x, plus h prime of y, and we know that this is equal to n. So which is x minus 2 cosine y, right? Because we said we will use this to find h of y, and when we cancel the x's, we will find h prime of y is equal to minus 2 cosine y, and we just integrate. H of y is minus 2, which is the integral cosine y. It is sine y. Okay, then. Okay, I will copy this. We find h of y, and just we will write. So I forgot what was h of y, minus 2 sine y. Okay, minus 2 sine y is equal to c, or let's write h of y c1. Okay, let's write c1 plus c1 is equal to c. Let's say c2, then we will write c2 minus c1 as c. So f is equal to minus cosine x plus yx minus 2 sine y is equal to c, is the general solution.